For the alkene reaction, so we've done hydrohalogenation, and the main thing there that we talked about was that it was a Markovnikov addition, and the Markovnikov addition means it's a carbocation mechanism, and whenever we have a carbocation mechanism, you always have to be ready for rearrangement, okay? And I'll go over that in our notes also, but I've written the characteristics over here, so you kind of know what to look for, okay, in all of these reactions. Then you have halogenation. We did halogenation, so you're just adding chlorine or bromine. Now, we don't usually add fluorine or iodine this way. Fluorine is too reactive, iodine is too slow. So we're kind of like with chlorine and bromine, we're in the Goldilocks region, so that's kind of works out for us. And also because chlorine and bromine are synthetically more useful, okay? If you think about it, the hydrohalogenation, the first reaction that I have here, or that we learn in alkene reactions, if you think about it, this is actually an alkyl halide, right? So you're making an alkyl halide, which is then used for substitution reactions. So when we did substitution reactions and elimination reactions, all our substrates were alkyl halide. Everything I'm talking primary halide, secondary halide, but I never really talked about how you make those halides, right? So sometimes, yeah, you can just order them from the store, that's fine, but even they have to make them, okay, somehow. So how do you make them? You make them using alkenes, okay? And remember, I also mentioned that a lot of alkenes are actually natural products. So you get them in nature. And then in some cases, you have to synthesize certain things anyway, all right? But otherwise, this is how you would make an alkyl halide, and then you can go on to do substitution reactions with it, okay? So what I'm talking about here is a multi-step synthesis, okay? And now you're getting to a point when you can actually do multi-step synthesis. You can start doing it. I'm going to introduce that to you today, okay, after we do all these reactions. So that's hydrohalogenation. Then halogenation is when you add two chlorines, okay? And we will do this reaction also again, not next week is Thanksgiving, but after that, all right? So this one now I wrote over here, this is an anti-addition, and I showed you the mechanism, and again, I'll go through the notes also. Hydrations we have to do today, okay? The halohydrin I already did because we did chlorination. So, but technically halohydrin I should cover after hydration, okay? So you also have hydration under your belt, but we have three hydration reactions. One is the H3O+, then oxymercuration, hydroboration, we have to do that. We have to do reduction, and then we also, of course, have the second page, okay, which is also a lot of reactions, okay? But here is the deal, okay, with all these reactions, and I'm going to be upfront with you. I don't do all the mechanisms. We can, you know, say a sigh of relief over there. So I do some of the mechanisms. You can find all the mechanisms in Klein. Klein covers all the mechanisms, okay? So I don't have to. The mechanisms that I cover are going to be the carbocation mechanisms, okay? Because the carbocation mechanisms are the ones that give us different kinds of products, okay? Or in cases where I need to explain certain things, okay? Like in the halogenation, I needed to explain to you how you get anti-addition, all right? So in those cases, I explained the mechanism, but again, I will not ask you for that mechanism in an exam. In an exam, I usually ask you for carbocation mechanisms, okay? So all the other mechanisms, they're good to know because you understand how the product is being made, all right? But honestly speaking, in an exam, I don't ask you all the mechanisms. It's not possible. You will go crazy also, and I'll also go crazy looking at all the mechanisms. So I stick myself to just the carbocation mechanisms. It's easy for you to understand and easy for me also to follow through. Okay, so that is the introduction here. Let's go ahead and look at our notes of what we did last time. And so here we are. So alkene reactions, this is where we started last time. And so I told you about the addition. This is all called a 1,2 addition Because you're adding on an alkene, and alkene is on 2 carbons, okay? So when you do the addition, you do addition on 2 carbons, not on the same carbon, okay? So then the first thing we did was hydrohalogenation, as I was saying, and we talked about the Markovnikov. Remember, Markovnikov is when hydrogen goes to the carbon with more hydrogen. That's what I've highlighted here in yellow for you. So a hydrogen goes to the carbon with more hydrogen. That's called Markovnikov. And now we understand why that happens. And why that happens is because of the carbocation formation. Okay, so the carbocation, the more stable it is, the better it would be. Okay, so that's why we get Markovnikov addition. So you have to write it that way. What you see in the box is how you should be writing it, okay? So what you see here in this box is really how you should be writing this reaction, okay? Like if every time we do this reaction, you don't have to show the mechanism, okay? Don't feel like you have to show the mechanism. I'm gonna show you some examples of what kind of problems you will get for these topics, okay? So that way you kind of know what to expect. Your self-study will also show you, okay, a little bit of what kind of questions. But anyhow, so the regioselectivity, again, a big word that really is just about Markovnikov, okay? So Markovnikov product and the anti-Markovnikov, which does not form, okay? But the thing is, if you wanted anti-Markovnikov, then what do? So we will talk about that later, okay? So we'll not forget about it. We will deal with it later. But right now, with this mechanism, we will only get Markovnikov, okay? Now, if something is symmetrical, okay, if you have a symmetrical alkene, then obviously it's not going to matter, okay? So I'm going to write this in a different color on this side. So if you had an alkene like this, in this alkene, the double bond is symmetrical, okay? Both of them have equal number of hydrogen. Or let me go ahead and add one more carbon to that, okay? Just to create a little bit of a problem, because, you know, I don't want you to feel like she gives us all the problems. She doesn't deal with problems herself. So here is a problem, okay? So now some of you may write that you're adding the Cl over here. So remember, it's 1, 2, 3, 4, 5. So I can add the chlorine on carbon number 2 or carbon number 3. Okay, so maybe some of you will write the first product, some of you may write the second one. In all honesty, you will probably get both products. So if you have a multiple choice question, make sure you select both of them, okay? Because there is no selectivity over here, because both of the carbons, 2 and 3, they are equivalent, okay? So there is no preference, there is no Markovnikov. You will get equal mixture, okay, of both of these products. So the Markovnikov you get only if the alkene is asymmetric, like it's shown over here with the cyclohexene, okay? So that's how you get this. All right. And again, feel free to stop me anywhere you want to. So then we talked about halogenation, and halogenation I mentioned to you is going to be an anti-addition. And the way the reaction works is that you form the bromonium ion. Once you have the bromonium ion, the Br minus, the bromide, the second bromide comes in and attacks from the backside like an SN2. And so you end up getting bromine on opposite sides. Okay, so you have to show me the stereochemistry. I did not show you the stereochemistry in this one, in the first one, because there is none. In carbocations, remember, because carbocations are planar, you don't really get stereochemistry, or sometimes you get a racemic mixture, okay? So that's not important there, but it's gonna be important over here, okay? And in some cases, it's not even important there. Let me tell you why it cannot be important in some cases. And let me go ahead and show that to you here, okay. So for example, if you had an alkene like this, and you were to do bromination on this one, okay? And sometimes I give the solvent, sometimes I don't. Don't be bothered by it too much, okay? Don't let that distract you. So in this case, when you're writing your product, this is your product. Oh, sorry, Br. So you know, and I know, I hope you know, that this carbon is not chiral. okay, because it's got two hydrogens. So which means that's not a chiral carbon. So if it's not a chiral carbon, really, how does it matter how I write my bromine? Okay, so honestly speaking, it doesn't matter. So if you forget to show me the chirality there, it's fine, okay? But for your practice sake and for your memorization sake, I will say just write the stereochemistry, okay? Every single time, because it's not really stereochemistry, it's just showing you that you're doing an anti-addition, okay? So that's what's going to happen. Now, if you write the other way, if you say, okay, you know, maybe we will get this product. So both of you are correct, okay? So don't fight with each other. You will get both of them, okay? And so which means you get the enantiomer also, okay, in this case. So hopefully you're thinking, do I have to give both the products? No, you don't have to give me both products. I just need you to know in your heart that you will get both products, okay? So even in an exam, hopefully in the quizzes that you will see, I don't say plus enantiomer. And if I do, just understand that it's just an enantiomer, okay? That's all it is. But you don't have to give me both, okay? I will completely understand what's going on. Okay, so that was the bromination or halogenation. And then we did the halohydration. Halohydration is addition of chlorine and water. So chlorine and water, now you're adding two things at the same time. This thing will always do this to me, right? One time it cannot work properly. Okay, there we go. So chlorine and water, or bromine and water. You can also do bromination here, okay? So bromine and water and chlorine and water. Again, you will have the anti-addition, so that's an important thing. The other thing about this is it's also a Markovnikov addition, okay? In this case, so I've shown that to you over here, that this is a Markovnikov addition. So one of the things that, you know, sometimes, you know, when you hear people say that, you know, organic chemistry, you have to memorize a lot. These are the things you have to memorize, okay? And you can, but the thing is, my point is that if you practice enough, then it becomes part of your life, you know? So when you go to the grocery store, when you're driving there, hopefully you don't have to put your maps up all the time, okay? Because now you really know how to go there. Nobody has to give you directions every single time. So that's kind of the thing with practice, okay? So if you practice enough, hopefully you'll be fine. Okay, so this was halohydration. All right, so now we'll go ahead and get started with hydration. Any questions, anything from anything that I've covered so far? Oh. Okay, hydration. So hydration, as the word says, is of course addition of water. Okay, so it's just not addition of water, because water is not going to do anything. Water is neutral, right? It's not either acidic nor basic. So generally we do hydration in presence of an acid. Okay, so we don't do hydrations in presence of bases. We do it in presence of acids. Now, this is an important thing, okay? And I mentioned that in my video also that I posted for you for elimination reaction. And I will say it again, that when you're working with positives, okay, make sure that you only have positives or neutrals. You should not have any negatives in there, okay? So you will see, as I'm writing the mechanism, there will be absolutely no negative charge here. There will be no anion. Okay, as I'm working through, it'll be either positive or it'll be neutral, okay? And you should work with only the things that I give you to work with. Don't work with anything, don't get anything out. If I give you H plus and water, those are the only two things you can work with. Okay, so let's write the mechanism for this one. So of course, the double bond is the base, and that's the acid. So that picks up a proton, and we know the proton, once it gets picked up, it's going to go to the carbon with more hydrogen, so you form the more stable carbocation. And once you do that, now the water will come in, because now water is the base. This is the Lewis acid now, right? First of all, this was the Lewis base, and this was the acid. Now the carbocation is the acid, and the base is the water. So now the base is going to go ahead and attack the carbocation. So oxygen is the one that's bonding. Please be clear. If you're writing the notes, and I hope you are, please make sure your bonding is good, okay? And when you write your mechanisms, please write them a little bit larger so it's clearer for you and clearer for me also. I give you enough space to write mechanisms. All right, so then you get something like this. Again, remember, this is called the oxonium ion. We have kind of talked about it before. Doesn't hurt to write the name again. Oxonium ion is whenever you have oxygen with 3 bonds on it. So now we just need to make sure that our oxonium ion is not stressed out, which means that we need to pick up this proton, okay, from there. So we have now an alcohol. So Markovnikov addition, carbocation, of course. All right, so Markovnikov meaning hydrogen goes to the carbon with more hydrogen. But whenever you have a carbocation, we're going to have issues, okay? And our issues go back to SN1, SN2 also, and E1, E2, okay? Because remember, we were forming Zaitsev products there. So again, that was a, carbocation issue. So here also, we're gonna have carbocation issues. So let's talk about what issue we have. And the issue is rearrangement. So let me give you an example of that. Whenever you have a carbocation, okay, and I've said this before also, and I'll say it again, I'll probably say it again. Just take a minute, okay, when you form the carbocation, just take a second and look around and see if there is rearrangement possible. Okay, now if you have a tertiary carbocation, you don't need to do that because there is nothing more stable than a tertiary carbocation. Okay, but if you have a primary carbocation, first of all, you should not be forming a primary carbocation. But like in the mechanism I gave you in the homework, you had to do that, but then you will do rearrangement. Okay, so if you form a secondary carbocation, look around, see if you can move anything to rearrange it in order to make it more stable, okay? So that's the one thing you should do. Second thing, you should also look for resonance, okay? And that's something I mentioned in the last homework also, that, just look around, see what is movable, okay? Because things are movable. And, some of you just wrote methyl shift over here. That doesn't work for me, okay? That it doesn't make any sense. What you have to show me is this arrow. That's what makes sense to me, okay? That this is a methyl shift. Just writing that this is a methyl shift doesn't make any sense to me, okay? So I don't give credit for that. So now what happens? You have a methyl group here, you have a methyl group here that you just shifted, and your carbocation is now going to shift over here. So that's the rearrangement that's going on, okay, in this. Now all we have to do is then add water. So the same process as we had before. Make sure your arrow is going from negative to positive, electron rich to electron poor, always. So there is that, there is this, and then there is the oxygen. Don't take any shortcuts until I tell you to do so, okay? So here, make sure that you have your oxonium ion, and then finally you will have the water pick up the proton. You can skip the second arrow if you want, okay? That you can do. I will tell you what you all did, and don't do that. Finish writing this and then I'll tell you. Okay. So here is what you all wrote for me, okay? So this is what we have. Let's say this step, I'm just writing again just to show you. And what you did is showed me that, oh, a proton is leaving to get OH. Again, this does not work for me, okay? Because I need to know how the proton is getting lost, okay? How are you losing it? Because a proton is not just going to leave by itself. okay? Something needs to come and take that proton away, all right? So which means that you need to have the water here, okay? That needs to come and pick up the proton. That's what you need to do, okay? So don't just write minus H plus. It doesn't work, okay? It's just take a little time and, you know, spend some time with the mechanism, and then you will understand what I'm talking about, okay? Because if I skip some of these steps, trust me, you will be so lost, okay? You'll be saying like, I don't know where the proton is going because I don't know what she did. So it's the same thing that I feel with you, okay? Is that, you know, just show me what is picking up a proton, what is attacking, how things are moving around, okay? All of that. Okay, so this is the mechanism if you had rearrangement, all right? And that's what's happening over here is rearrangement. And why did we have rearrangement? Because it was possible. Not that it's always going to happen all the time. It will happen only when there is a shift possible to make a more stable carbocation. And again, remember, what are the things you can shift? You can shift a hydrogen, you can shift a methyl group, you can shift a phenyl. Those are the only things you can shift, okay? You can't shift ethyl, propyl, or something like that. You can increase the ring size, okay? Which some of you did a fantastic job of that in your mechanisms, okay? So just show the bond shifting towards the carbocation. You can do all of that, definitely. Okay, any questions in this? I have one last thing to mention, okay, about hydration, because this is a very important mechanism. If you close your eyes and if you think about this mechanism, which I hope you are, and I want you to reverse this mechanism, just reverse it. And if you reverse this mechanism, which means that you're starting from an alcohol and you're ending up with an alkene. That was one of the reactions we did in elimination reaction. We did the dehydration of alcohols. Okay, you can look back, flip back into your pages and your notes, and you will see that. Okay, we did exactly the same reaction, except backward, which means that I started with an alcohol and we ended up with an alkene. The alkenes that we would always get from hydration is the Zaitsev product. We would never get Hoffman product, okay, from dehydration of an alcohol. Why? Again, carbocation mechanism. All right, so this reaction, now we're doing it forward, which means we're taking an alkene and we're adding water to it. In the elimination reaction, we started with an alcohol and we added H2SO4, concentrated acid, okay? So what I'm trying to say is that this reaction is reversible. So how do we do this? Let's say you have this. So if I give you H2SO4, you will give this product, because H2SO4 means that this is getting dehydrated. So you get an alkene minus H2O, right? That's what we did. Now, you can do this reaction by adding H3O plus, which means that this reaction is actually in equilibrium. Okay, because H2SO4, H3O plus, what are we talking about here? Both of these are acidic mechanisms. This means that this is dilute acid. The dilute acid here is H2SO4 also, okay, except it is diluted. So when we're talking about H2SO4, just H2SO4 generally means that it is going to be concentrated. If we don't write anything in front of H2SO4, it automatically means that it is concentrated. If we write H3O plus, generally that will stand for H2SO4. It will not stand for HCl. And let me tell you why it will not stand for HCl, because HCl is also an acid, okay? So here is your answer for HCl. Look what happens with HCl or HBr. If you have hydrogen bromide or hydrobromic acid, you will get halogenation. Okay, but we don't want halogenation when we want to make alcohol. So we don't use HBr or HCl as an acid. Okay, when we are talking about H3O plus, our H3O plus means that we are talking about H2SO4. All right. So just some things, over here to clarify. You cannot exchange, or use whichever acid possible. Phosphoric acid you can use, okay? So H3PO4 you can use, but you cannot use halogenated acids, okay? So HCl, HBr, no, okay? You can't use those because then you will end up getting hydrohalogenation. So you can't do that. Okay, so this reaction is in equilibrium, all right? So I have not been writing equilibrium because I did not want to create any issues with you. And it is important, but it's not that important, So the forward reaction is going to be H2SO4. And the backward here, this arrow over here that's going backward, that is H3O plus then, okay? So which means that anything that we talk about equilibrium kind of falls in here. I usually don't give you too much confusion in this, so I don't ask you in the middle of equilibrium what's going on, blah, blah, blah. I don't do all that kind of stuff, but I just want you to know that we did this reaction with the dehydration, okay, to get an alkene. So let me see if there's anything else I need to mention over here. I think that is about it. Yes. So one thing one thing more, okay, that we need to talk about over here is retrosynthesis. Okay, retrosynthesis means going backward. All right. So if I say to you that, okay, let me not take this one. I'll take another one. Here. So let's say that I want to get this alcohol. And I ask you, what kind of an alkene do I need? Remember, this is a retrosynthesis arrow. I want you to get comfortable with it. So what kind of an alkene do I need in order to get this alcohol? Now you know that with an alkene, you can use H3O plus, right? In order to get the alcohol. So that much you know. So now it's just a matter of, okay, what alkene can you use? So alkenes possible because your alcohol is on carbon number 2, your alkene can be here or your alkene can be here. Okay, you can have 2 different alkenes. But then the question is, which one will give you the maximum product? Can anyone try to answer that for me? Which one will give you maximum product? The first one or the second one? You can type it in the chat if you feel like. Which alkene will give us the maximum product? And let me make this a little bit more challenging for us. Okay, so I'm going to add 1 carbon here. There. Okay, go for it. I'm waiting for the chat. First one. Anyone else? So because I changed the alkene, if you want to change your answer, you're most welcome to change your answer if you want to. Anyone? More? Ah, one more. My chat lit up. First one. Okay. All right. Well, that's okay. Since this is our first retrosynthesis that we are doing, it's actually the second one. If you do hydration on the first one, then you can get, this is 1, 2, 3, 4, 5. So you can get an alcohol either on the 3rd carbon or on the 4th carbon. So you get a mixture. But if you do hydration on the second one, then you will get that only over here. This is the only product you're going to get. In the first one, both of the carbons 3 and 4, they're equally available. There's no preference. But in carbon number 1 and 2, in the second one, they're not equal. Okay, carbon 2 is preferred. So if this is the alcohol we want to make, then this is the alkene we should use. Okay, so you have to be careful, all right, what kind of starting material you want to start with to make an alcohol. Okay, this is just the beginning. Okay, we have so much more retrosynthesis to do, but just a little bit of an introduction of this to you. Okay, so this was hydration, but here's the issue with the hydration, as I said. First of all, you only get Markovnikov. Let me just scroll up here real quick. All right. So two issues that we have with this reaction with taking an alkene and just treating it with acid, dilute acid, is that you get only Markovnikov addition. And number two, the rearrangement is possible. Okay, so you got two issues. What if you want an anti-Markovnikov alcohol? What if you want your alcohol to be on the carbon with more hydrogen, right? So what if you want anti-Markovnikov? And the same thing with the rearrangement. You don't want that, problem that you're going to get rearrangement. Okay, you want your alcohol to, just be where you want it to be. All right, so for that, we have reagents, okay, that can do it. So the first one we're going to learn about is oxymercuration. And oxymercuration is this. So you take an alkene and you treat it with what is called mercury acetate. And just write it for now, and I'll tell you what this all means. And usually there is a hydroxide that goes here. And you get an alcohol. Please make sure that your bond is from the carbon to the oxygen and not somewhere in the middle, and not to the hydrogen. So this is still Markovnikov. I'm going to write a short form, okay? Markovnikov product. This is still Markovnikov. But the best part about oxymercuration is that there is no rearrangement. I'm not going to write the mechanism. You can check the mechanism in Klein if you want to, but this is a little bit different kind of mechanism, so which means no carbocation mechanism. Okay, so this one will give you only the Markovnikov product, but advantage, no rearrangement. So which means that if you had this alkene and you were to use mercury acetate, you will not get any rearrangement, but you will get the Markovnikov alcohol. So let's talk about the reagent for a second. So first of all, there are two things that I have written over here. Okay, number 1 and number 2. Generally, when you do any kind of a reaction, you have to have a reagent. That reagent is going to give you the product. Okay, the second part of any reaction is called the workup. All right. So you all are in the lab, and right now you're probably doing all sorts of synthesis, and maybe you're also in your last synthesis. Okay. So you will see that when you're doing those syntheses, the SN1 and the SN2 that you have done, the first part is adding the reagents together and then letting the reaction happen. So when you did the SN2 with the sodium bromide and all that, you let it reflux for an hour or so, the reaction happened, and then you had to add, I think another sulfuric acid. So then you add sulfuric acid and then you wash it. That part is called the workup, okay, of any kind of a reaction. So what is happening in the workup is you're removing all sorts of ions from there, because you will have ions floating around, okay? So you're removing the sodium ions, you're removing any of the excess bromide ions. So you remove all of that. Then you wash with water. So which means that you remove acids also now at that point. And then the last thing you do is dehydrate, which means that you get rid of the water. So now you only have your product in the end. So practically speaking, that's what you do. When we write our reaction like this, like 1 and 2, the 1 generally indicates that that is my reagent. I'm going to start my reaction like that. Once my reaction has gone on for a while, so which means that it has progressed, so then I will add 2, which is sodium borohydride and hydroxide, which is usually sodium hydroxide. So I'm going to add that, and that will give me the product. Okay, so sometimes what happens is that your intermediate is going to look really weird. And if you look at the intermediate for this one, it's going to look like this. I think it has mercury and stuff like that, okay, in the intermediate. That's not your product. But once you add the sodium borohydride and once you add the hydroxide, this will cleave off and then the oxygen will get protonated. Okay, so then you will get your alcohol. So that's the workup. Now, do you have to know all of this all the time? No, I need you to understand that if you see these 2 things, then that's what they mean. Then the second question, of course, you might be thinking, do I have to write both of them? It'll be nice if you do, but if you just wrote mercury acetate for me, I'm fine with that also, okay? Because a lot of times we can't remember the entire reagent sequence, so that's fine. You just write mercury acetate and I'm fine, just provided you write me the correct reagent, all right? So now let me tell you what this mercury acetate thing is, okay? Because I wrote HgO AC2. So this is a diacetate, but the AC is what I need to explain to you because this is our shorthand. So you know the shorthand we use for methyl ethyl propyl, right? MEETPR, BU for butyl, and so on. So AC is like that also. So AC group is the acetyl group, and the acetyl group is this, COCH3. This is called acetyl or acetyl. It depends on your pronunciation, whatever you want to call it. Acetyl group, acetyl group. So that's the AC group. So now let me put it into context for you so you will see where you have seen this before, okay? So when we write OAC, OAC will mean that you have O, CO, CH3. Okay, so that's what the O will mean there. Now, let me put this even in more context for you. And you don't have to write all of this, okay? Because I'm just explaining this to you. So you understand the organic shorthand. So you've seen this before. This is acetic acid. Okay, CH3, COOH, that is acetic acid, which you have seen before. So the shorthand for acetic acid is actually this. And the acetyl group is the COCH3 then. Okay, so you will see this a lot in organic too, because we deal with carbonyls a lot in organic too. Right now, this is the only place I think for now. Okay, so that's it about oxymercuration. I don't have anything more to say. So that's Markovnikov, no rearrangement, you know, that's our wonderful oxymercuration. Now for the third reaction, which is called hydroboration, I'll just start on a new page. Hydroboration is a little bit different because so far what we did, when we did the first reaction for hydration, it was an acidic medium. In acidic medium, we had carbocation, we had Markovnikov. When we did oxymercuration, we got rid of one of the problems, which is the rearrangement because of carbocation. But we still had one problem. It's not a problem. If you want Markovnikov product, that's fine, you know. But hydroboration actually takes care of the other problem or other issue, which is that it's one will give anti-Markovnikov addition. So now if you had this kind of an alkene, now if you treat this with borane, BH3, and just again, write the reagent and I'll explain it to you. So now remember, this hydrogen is the carbon with more hydrogen. So now your alcohol is actually going to go here. And your hydrogen will go to the carbon with less hydrogen. So this is the hydrogen that has added to the carbon with less hydrogen. I'm going to remove the hydrogens, or at least this one there. So this is anti-Markovnikov. Hydroboration was developed, I think is it in Purdue? I think it was in Purdue. And the scientist who developed these reagents, H.C. Brown, this is like one snowflake in a snowstorm. Okay, so he's got tons and tons of reagents using boron. So he's famous for boron chemistry, and so he developed a lot of reagents that really help in making alcohols and also different boron reagents. Okay, so this is BH3. And let me explain this reagent to you. So BH3 is boron, as we call it. So borohydride, or you can't call it borohydride. It's actually boron only. So BH3, if you see in the periodic table, it's actually in group number 3. And BH3 means that it has only 6 valence electrons, which means that it is lacking electrons, right? So if it's lacking electrons, it means it's incomplete valence shell, all right? So if it is an incomplete valence shell, it's actually very reactive, okay? When we learned about this in chapter 3, when we were talking about Lewis acids, okay? So boron is actually a common Lewis acid because it can accept a lone pair of electrons, okay, from any other base. So here what happens, and if you see this dot that I've drawn, the colon that I have drawn here with the THF, that's actually a lone pair of electron that is being shared with THF. So what the heck is THF? THF is called tetrahydrofuran. There are so many things that you learn, not just the reaction itself, but also about reagents. So THF, tetrahydrofuran, is actually this compound, which is an ether. If you did the worksheet that I had for you in SN1, SN2 reactions, because I had 2 worksheets there for you, one for substitutions, one for elimination, and also substitutions, you will see that I gave you to make this ether in there, all right? And Klein has this too, so make sure you look at this. So THF is a cyclic ether, okay? And this is what it is. And really THF, I mean, we're going to learn about ethers in the next semester, but ethers are actually very unreactive. So they're very good solvents, okay? And so what's happening here is that you have the 2 lone pair electrons on oxygen. And what happens is that the BH3 will share those electrons. It's not reacting with it. It is kind of just holding on to those electrons. That's all. So it's just stabilizing the BH3. That's all. Okay. So it's not a compound. It is just an association. Okay. So once the reaction is happening, that the THF is going to go away. All right. It's just the solvent there. So don't be bothered by THF. And if you forget to write THF, it's fine. I will not penalize you for that. You can just write that you use BH3, number 1, and number 2, H2O2. That's good for me. Okay. This pair is good for me. H2O2 is, of course, hydrogen peroxide. Okay. So remember again, the first part here, number 1 is the reagent. Number 2 is the workup, okay, of the reaction. All right, so what's happening here? We are getting anti-Markovnikov product, okay, in this case. So this is all a different kind of reaction. So the way this reaction works, you really should see the mechanism for this. I don't want to spend too much time on it, but really what happens is that you end up getting an intermediate. Let me erase this. I don't need this. You get an intermediate like this, all right? And then there's this 2 hydrogens more. And actually boron can react with 2 more alkenes. Remember, alkene is the Lewis base and BH3 is the Lewis acid, okay? So that's the reaction that's going on here. So it can react with 2 more alkenes to form a complex. So once that complex is formed and then the sodium hydroxide comes in, well, the sodium hydroxide cannot access this carbon because of steric hindrance. So the only carbon it can access is this one. Okay, that's outside. And so because of that, you end up getting anti-Markovnikov products. Okay, so that is kind of in short form the mechanism for this reaction. Again, You can look at it, but you don't have to memorize it, okay? So you just have an idea of how this is working. But that's the reaction. I will give you a hint, and I always say this, and sometimes you remember, sometimes you don't, and that happens, that's fine. Whenever you see H2O2, that means something is going to be anti-Markovnikov. You will see that in future also, okay? So it's kind of a little hint that, this is what's going on, but anyhow. Okay, so those are the three hydrations that we have over here. One is with H3O+, one is the oxymercuration, and then the last one is hydroboration. Now, again, with the hydroboration, if you have an alkene like this, it honestly does not matter. Okay, I'm going to add one more carbon so that alkene is asymmetric. Okay, asymmetric meaning that you have two carbons here, but only one carbon here. So now if you're using borane, now you can get two products, right? So you can get an alcohol here, or you can get an alcohol here. There is no preference, okay? Because the alkene, it's symmetric in the hydrogen, but it's asymmetric on either side. Okay, so the alcohol can go on either carbons. Okay, so 1, 2, 3. So it can either go on the third carbon or the second carbon. So you can get both products. So you really have to be careful when you choose your starting material that you don't end up getting too much of a mixture, okay, of products. So you have to be careful with that. Okay, any questions? All right, then. Next reaction is hydrogenation. Hydrogenation is neat. I don't think you will miss this at any time. I don't think you miss any of these reactions usually. Alkene reactions are really fun. It's also a very good introduction to what's coming ahead. Okay, alkynes are going to be very similar, and then when you get to alcohols and all that next semester, it's all going to be very similar. Okay, so hydrogenation is when you're adding hydrogen. So here what you do is you take an alkene, and that's all you're doing, is adding hydrogen. Now this addition, right now, it has absolutely no meaning whatsoever, but I'm still going to go ahead and write it. It's a syn addition. Syn addition meaning that the hydrogen is being added on the same side. This is not a chiral carbon. Neither of these carbons are chiral, so it doesn't really matter if you show the stereochemistry or not. But sometimes when you have differently substituted carbons, then it's going to matter. Okay, so in those cases, you have to know, okay, that you're doing a syn addition. So maybe when you write the products, just go ahead and write the stereochemistry, so that way you have memorized it. Okay, that kind of helps with that. Okay, so there's only one problem with this reaction, is that hydrogenation does not really work like this. Okay, so it's not like you can take an alkene and just add hydrogen to it. Hydrogen is the lightest gas. Okay, on the periodic table, it's even lighter than neon. Okay, neon has a mass of 4, but hydrogen has only got a mass of 2. So hydrogen is the lightest gas. So to catch a hydrogen molecule and to be able to do this reaction is really, really hard, okay, to do. So what you have to do is add a catalyst for this. And the catalyst is usually a heavy metal. So you either use palladium or use platinum, okay, which you will find in the transition metals kind of at the lower side. So you use palladium or platinum, and what the palladium or platinum will do, and I'll cover this a little bit more when we get to alkynes also, is that if this is the palladium surface, what it ends up doing, it ends up what's called adsorbing. If you don't remember this now, don't worry about it, okay? Because I'll talk about it again in alkynes where it is actually a lot more important. So it will adsorb the hydrogen, so which means it catches it. So once you have a heavy metal or something, a surface that actually holds on to the hydrogen, Now the alkene can come and now it can pick up the hydrogen, okay, and do the reaction. So that's really what the mechanism is like. And because it's picking up from the same side, you end up getting a syn addition, okay, for this. So this is hydrogenation, and that's all there is. There's only one problem with hydrogenation, and that is that hydrogen is very explosive. So usually when you have to do hydrogenation in labs, people don't store hydrogen in their labs. You have to actually have kind of like an outhouse for this. So there is either it's on the top of the building on the roof, or it's outside the building completely. There is another room for hydrogenation. So practically speaking, you actually have to go outside the building or on the roof, to do hydrogenation, because it can be dangerous. So you have to be careful. That's all I'm saying. All right. Stop me wherever you want. So now we're going to talk about diols. We're going to do two diol formations. So diol is dihydroxylation, which means two OH groups. So two alcohols. So previously we just had the one alcohol, right? Now we're going to have two alcohols, okay? And these things are also extremely common. And when we get to the alcohol chapter next semester, if you're in my class, we will get to talk about alcohols as well. And, this is an important reaction. And also why it is important. So I'm going to give you two reagents here. I think Klein only has one, but I give you two. So the first one is osmium tetroxide, OSO4. I have one other disclaimer to make. And the disclaimer is actually for the workup. Okay, so I was explaining to you about the workup. So for example, in pH 3, you're using hydrogen peroxide and sodium hydroxide. In oxymercuration, you're using also sodium borohydride. So sometimes what happens is that the workup reagents can be a little bit different, okay? The reagent is the same. So osmium tetroxide is the same, but sometimes the workup reagent can be a little bit different because the workup reagent is not really doing anything to the reaction. It's only helping to finish the reaction. So it's not the reagent itself, okay? So if you see something in there, don't get too worried, okay, as to, oh my God, this is not what I saw. Just focus on the main reagent. And if you see the main reagent, then, then you're okay. All right. So what we get here is going to be a diol. And that diol is also a syn addition. Osmium tetroxide is like this. This is what it looks like. So you can see kind of what happens, okay, is that the alkene will come like this and then pick up the two oxygens, and then you have the cleaving of the double bonds with the oxygen and the osmium, and then you end up getting your diol, okay, at the end. So again, you can look at Klein for the mechanism if you want to, but that's kind of how it works, okay? And that's how you get the syn addition. I'm going to go ahead and erase this for now. So that's one thing. And I think the workup reagent here is usually like sodium hydrogen bisulfite or sodium hydrogen sulfide, NaHSO3. But if it is not, don't worry about it. It's okay. It's not a big deal. You can also take an alkene, treat that with KMNO4 at RT. RT means room temperature. And you will get the same product. Also syn addition. So MnO4, KMnO4 is the same kind of thing where you have Mn and oxygen, 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 oxygen. The potassium is right here. So you get a similar kind of a syn addition, okay? These reactions are also oxidations because you're adding oxygen into the product. And the reason I'm mentioning this to you here is because this reaction is a qual test. And I don't know if you've already synthesized the alkene or not in your lab, but you're going to do the qual test because now what you end up getting as the other product is actually MnO2, and you will see that I have not written that anywhere else. What other product you're getting, I have not written because it's not usually our concern that much, but here I am because it's a qual test. And this is a brown precipitate. KMnO4 is a purple solution. So when you add KMnO4 to an alkene, you will end up getting a brown precipitate because the KMnO4 will react with an alkene. If you had an alkane, there'll be no reaction. Your solution will still stay purple. Okay, so it's a qual test. So what's the difference between osmium tetroxide and KMnO4? Why do you want to use one or the other? So osmium tetroxide is actually it's a transition metal, but it's also very expensive. Okay, so osmium tetroxide works fantastic. All right, it's really a good reagent. It's an excellent reagent, but it's also very expensive. Okay, and the back when I was working with it, I think I had like, I don't know, 5-gram bottle, and a 5-gram bottle would be like $150 or something like that. So it's a pretty pricey kind of a reagent. And 5 grams doesn't do much, you know, I mean, it's just a small amount. KMnO4, on the other hand, is dirt cheap. Okay, so you can get as much as you want. The only thing is it's a messy reaction because it's purple and then you get the precipitate. So the cleaning up is a little bit of a problem. But if money is an issue, then KMnO4 is better for you. If money is no issue, osmium tetroxide is good for you. The other problem with osmium tetroxide is actually it's very toxic. Okay, 2 minutes of exposure to osmium tetroxide, not 2 minutes, okay, 5 minutes, because yeah, it can cause death. Okay, so you have to be very careful when you're working with certain reagents. You have to, you have to read about their safety. Okay, and when you go into the lab and we have you look at the safety data sheets and tell you all about the safety of all the reagents that you're using, it's for a reason. And so osmium tetroxide is actually a very toxic reagent, so you have to be very careful with it. It's fantastic reagent, very toxic. All right, you decide your poison. Okay, so that is dihydroxylation, but this one is a syn addition. Okay, both of these reactions are syn addition. So now I'm going to tell you one with the anti addition. Anti-addition, oh my God, my handwriting is so fantastic. There you go. Okay. Anti-addition would be if you take an alkene and just write the reagent MCPBA, and I will explain what that is in just a second, and you end up getting what's called an epoxide. Don't worry, you keep writing, okay? I'm just going to make it smaller so I can write this reaction in one line instead of 2 lines. There, MCPBA. So epoxide is something like this. It's a small 3-membered ring. You treat that with H3O plus acidic medium. So again, dilute sulfuric acid. And now you end up getting an antidiol. So MCPBA, metafluoro per benzoic acid, MCPBA. At this time, I will just write MCPBA for you. So you don't have to memorize the whole name or the structure for it too. So here is the structure. It's a benzene ring. It's a benzoic acid. So, and I know you've used benzoic acid in your labs already, so you know what that looks like. Benzoic acid has 2 oxygens. When you have perbenzoic acid, it has 1 extra oxygen, okay? So don't be fooled. I have drawn 3 oxygens here in purpose. Per means many, okay? So just like you have water, and then you have H2O2. So this is just water, but this is hydrogen peroxide. Per meaning many, many, the maximum amount possible. Okay, so that's what happens with the perbenzoic acid also. Okay, you can also have peracetic acid. Peracetic acid would be, again, just 1 more oxygen in there. Anyway, so you take an alkene, you form an epoxide, and when you treat it with acidic water, that will give you anti-addition. Okay, so you still get a diol, but now you get an anti-diol. This reaction also you will do in organic 2. We're going to write the mechanisms of all of this in organic 2, not right now. At this point, you just need to learn that this is an anti-addition. That's it. Where do you see diols? By the way, diols you will see in carbohydrates, okay? That's why we are talking about the synthesis of diols, okay? Because all of the carbohydrates are all alcohols. Questions, anything? Okay, all right. So that brings us to an end. I'm going to skip one reaction, okay? Just let me show you which one. The carbene addition, okay? I'm going to skip that reaction. I don't think you need it, all right? It just becomes too much. The carbene reaction for us at this point has no practical purpose. Okay, so I'm going to skip that one completely. We've done all the diol synthesis now, all the 3 that are given on the top. The last reaction to do is the cleavage, okay, which is very short also. All right, just wanted to let you know that you can cross that out of your list. Okay, so the last thing about alkenes, depending on how you feel about things, is what's called oxidative cleavage. And I'll tell you what I mean by my snarky remark there about how you feel about things, because it's kind of a fun thing to do. Cleavage means breaking of bonds. This one is literally breaking of bonds. Let me just mention something, okay, that bothers me. And I know that you probably think that I'm so particular about things, but you know, our words matter. You know, when we communicate, when we say something, all of that matters how we say it, okay, and the words we use. So this is something that I hear a lot, okay? So for example, if you're writing the mechanism for this, and I hear this all the time, and maybe it's, you know, the other professors are also using this, I'm not sure, is that when we do this kind of a reaction, you know, we've done hydrohalogenation, is that I will hear somebody say that the double bond is being broken. But the double bond is not being broken here, okay? It's not being broken. This is an addition reaction. So when you do this, you're actually doing this, right? So you're creating a carbocation. So the proper term to use it is that the double bond is adding on to the hydrogen. The double bond is not breaking. Yeah, it is true that in the final product, you don't have the double bond. Okay, so yeah, definitely the double bond is not there. But when you say that double bond is breaking, it means it's breaking like this. Okay, so you want to be careful when you write your mechanisms and when you're talking to each other. And I hope you're talking to each other and explaining the mechanisms. Use the right terms. Okay, so that way you will also understand the reaction much better. Okay, so don't say that the double bond is broken. Say the double bond is adding on a hydrogen because it is an addition reaction. Okay, because the oxidative cleavage is really where you break double bonds. Okay, so it's two different things. Okay, when we do this, somebody's having really fun with their Wi-Fi today, coming in and out. Okay, so let's talk about this breakage of bond over here. So if you take an alkene like this and you treat it with ozone, ozone is 3 oxygens, right? Oxygen by itself is O2, but ozone is O3. So if you do this, then the double bond is going to cleave. So now it really is going to break. And at the double bond, you're going to get an oxygen on either side. So I'm going to just write it just the way it is written right now. So you can see that if you push the oxygens together, you'll get the double bond back. Not that you get it back, you don't. Okay, but I'm just saying that's kind of what it looks like. You don't lose any carbons. Okay, so 1, 2, 1, 2. All right, so 1, 2, and 1, 2. So you still have both the carbons. You have all the carbons. It's just that now you have 2 fragments, okay, in here. So this is ozonolysis. Actually, I should write it on the top here. Ozonolysis. Lysis in bio, I think, means breaking apart. And in this case, you also have a workup, okay, which is DMS, and that is dimethyl sulfoxide. Sulfoxide is this, and dimethyl meaning this. If you don't know the structure, don't worry. If you don't remember is dimethyl sulfoxide, don't worry. It's fine. If you don't remember DMS, don't worry. Just write ozone for me, and I'm fine. When you start doing so many reagents, it's not possible to remember every single detail, okay? So don't push yourself. Whatever is above the arrow is the most critical thing, okay? Whatever is below, I can excuse that, all right? But above the arrow is the most important one. So this is ozonolysis. So what's happening? The double bond is literally breaking, okay, in here. So let's do another one. And in this case, I'm going to take an alkene that is asymmetric now. So in this case, when you do ozonolysis, again, you're going to break, cleave it. And now because you have carbon here and a carbon here, so now you get this. And I'm saying this, but I'm going to go ahead and put words because you know what functional group that is. This is a ketone. This is an aldehyde. In the previous one, we got both aldehydes. So depending on your starting material, you can get a ketone or you can get an aldehyde. Now, again, you want to be careful when you do these kind of reactions is because you don't want too much of a mixture, you know, for products, depending on what you're doing. Sometimes, you know, these reactions are done for analysis sake, so you can figure out how many double bonds you have. Okay, so for example, you can take something like this. And you can cleave this. So I'm going to pause the recording for a bit, but I want you to go ahead and write the product, okay, for this. Okay, so breaking it here, And what I meant by keeping the same structures, keeping the same skeleton, I meant this. So keep it like that. Here is the double bond. Here is the double bond, right? That broke. And then here is your bottom part, not your bottom, the structure's bottom part. Okay, and then there is that. I want to make sure that I keep my bond lengths good so it doesn't look too awkward, although it's going to look awkward because I've added the oxygens in there. And then I'm going to have a ketone over here, and then I'll have this carbon, right? So that's an oxygen. So when you have substitution on both sides like this, you will get a ketone. And then when you have a hydrogen here, then you get an aldehyde. Okay, this is also an aldehyde because there are two hydrogens here, so that's also an aldehyde. So depending on how substituted the alkene is, you can get ketones and aldehydes. So this is a very typical question that I give you an alkene and then you just have to cleave it, okay, and show me all the different carbonyls that you can get. Now, I want to ask you for a favor for me, okay? So this is an important thing for me. Usually nobody pays attention to this part because I don't know what happens, you know, when you start writing your products, something happens and then, you know, you just forget what I told you, okay? And what I'm telling you, it's such a small thing that, you know, it's very easy to forget that, okay? So I'm going to write this reaction again. I'm going to write this one again. Poop, right on the other side. It's on the top. So this one, okay? So this one I'm going to write again, and I'm going to cleave this again over here. So what I want to show you is what I would like you to do for me. I mean, it will really make me happy. Sometimes when you write things, it doesn't make any sense, okay? So like this one will make sense. So here, of course, you are cleaving here. So oxygen and oxygen on both sides. So oxygen on the left-hand side gives you a ketone. And then what you do is you do this. And you're probably thinking, what's wrong with this? This has it. This is it. But my favor that I would like to ask you is please draw the hydrogen. Because it's an aldehyde, because it's a functional group. We draw functional groups and we draw all the hydrogens in the functional group. Just like an alcohol, you will always write OH for an alcohol. So an aldehyde is a CHO. So why do you skip the H of the aldehyde? Okay, so please write the hydrogen. I would really, really appreciate it if you do that. If you don't write it, it doesn't mean it's wrong. It just looks awkward. Okay, and it just, I don't know, it just doesn't feel complete. Okay, that's all. And this is what I get for this one, right? This over here, this is what I will get. And I'm like, what the heck is this? I have no idea what this is. All right, so this one I will totally mark wrong because I have no idea what this is. So unless you write the hydrogens for that one, I will not accept it. Okay, so just get into the habit of writing all the hydrogens on the functional group. Okay, you will see that your life will also be good. Okay, with that. Okay, so this is what happens when you do ozonolysis. Now you can also treat this with KMNO4. So let's take this alkene. This is a diene, which means two alkenes. And if you treat this with KMNO4, I want to remind you, we just used KMNO4. We got a diol, but that was RT, room temperature. This is with heat. So I have to tell you that this is hot KMNO4, or there's heat there, or it's high temperature, because the reactions are different. If you use KMNO4 at room temperature, you get a diol. If you take KMNO4 and you heat the alkene, now you will start cleaving it. Okay, so now you break the double bonds. But the interesting thing here is that you don't get aldehydes and ketones, you actually get acids. So again, same thing. I will maintain the skeleton, so you don't feel like, you know, I'm missing carbons or anything like that. Still have 6 carbons, but now my functional group here is a little bit different because now I have acids. So that's the difference between ozonolysis and KMNO4. Okay, is that KMNO4 is stronger oxidizing agent than ozone. So because it's a stronger oxidizing agent, it gives even more oxygen to the alkene. Okay, ozone gives only 1 oxygen, but KMNO4 gives 2 oxygens. This was the last reaction. This is it. But I do want to do some reactions with you, okay? So I know it's time for our break, but I'm not going to give you a break because I'm going to just go ahead with 10, 15 minutes more of practice so you have an idea. And of course, since it's being recorded, you can always listen to it again. So that way we'll be done with the class, okay? So you don't have to come back after 5 minutes. So I want to do some examples here with you as to what kind of questions you're going to get, okay, for alkenes. Because in alkenes, what you've done is you've learned a lot of reagents, all right? You've also learned a couple mechanisms. The mechanisms were the carbocation mechanisms, all right? So that you will have to practice, of course, and I think you're getting some practice even with the SN1, SN2. So now I want to focus a little bit on synthesis, okay? Which synthesis just means stepwise synthesis, okay? Synthesis means no mechanism. It doesn't mean that you should not know what kind of addition you will have. So for example, you have to keep in mind that whether you have Markovnikov addition or is it anti-Markovnikov, those kind of things you have to keep in mind. Is it syn addition? Is it anti-addition? What's going on? Okay, all of those things you have to keep in mind when you're doing these kind of synthesis. But the only thing is you don't have to write detailed mechanisms. Okay, so for example, if you have something like this and I ask you to give me the product, like what is this? Let me write a few reactions, okay? And then we'll go over them. I'll put the question marks for where I need the answer. So if you're writing, I have to scroll down so I can write some more. And one more. Okay. What I've written so far, this is one-step synthesis, okay, which means there's only one step in this. And you've done these reactions before because I asked you that in SN2 reactions also. So I gave you those one step in the E1, E2 homework that you just did for me. So let's go through all of this. If you have a different color, pick a different color pen so you can write the products. If you already know the products for this, please go ahead and write them. Otherwise, follow me, okay, with this. So The first one we are doing is addition of HBr. Addition of HBr on an alkene is a Markovnikov addition, so which means hydrogen goes to the carbon with more hydrogens, which means my Br is going to be here. There's no other stereochemistry here, so I'm fine. Now, in a lot of these cases, the carbon chain does not change, right? Unless there is some rearrangement, which this is not a mechanistic question, so that's not going to happen, which means your skeleton of the carbons is remaining the same. The only thing you're focusing on is the double bond, okay? So focus on the double bond, see what it is, see if it is symmetric or asymmetric, because if it is symmetric, it's not going to matter too much where you add stuff. But if it is asymmetric, it's going to matter a lot. Okay. So in the first one, it did matter because that was Markovnikov addition. In the second one, it doesn't matter because this is not a Markovnikov addition thing. This one is more like an anti-addition thing. So it's bromination. So bromination, I will just write this. Now, if you write the other one, which means the top one is going backward, that's fine too. That's okay. Because you will always get an enantiomer. And if it helps you, go ahead and write plus enantiomer. But really, otherwise, you should know in your heart that if you're getting one, enantiomer, you'll get the other one also. The third reaction is ozonolysis, which we just did. So all we have to do is cleave from both sides. So now there's two different ways of writing this. I'm just going to write the simplest way. Okay, and the simplest way is that here is an oxygen, hydrogen, hydrogen. Don't forget the hydrogens. And 1, 2, 3. So the middle fragment is 3 carbons. So 1, 2, 3. And then I'll have the oxygen, hydrogen, don't forget, aldehydes. So both aldehydes. Because the double bond is not that substituted to give you a ketone, okay? So it's aldehydes, and then you have an aldehyde on the right-hand side as well. So there's that, and then make sure you draw the hydrogens. So you end up getting 3 products in this case, okay? If you want, you can write plus in the middle. If you don't, that's okay also. Now, this is a kind of retrosynthesis. The next 3 that I have is retrosynthesis. I could have written the BR, the product on the left-hand side and given you a retrosynthesis arrow, but we'll just keep it simple for now. So here I can see that I have bromine and alcohol, which means that I am adding bromine with water. Now, I have a habit of writing this way. Like I just wrote with this dash line over here. That just means that I'm adding 2 things. Okay, if you're more comfortable, you can also write comma and then H2O. Okay, it's both of them are the same things. And then of course I need an alkene. My alkene is going to be here. Actually, it can be anywhere because it's only one alkene, so it doesn't really matter where I put the alkene. Stop me wherever you want to. I always say that. Nobody stops me, but stop me wherever you want. Okay. So the next reaction, it says 2 moles of this ketone. So the only way I can get 2 moles of a ketone is by ozonolysis. Actually, I can get it by KMNO4 also, okay? But I'm going to write the ozonolysis first. And again, as I said, you don't have to write all the reagents. If you just write O3, I will be happy with that, okay? So you don't have to remember DMS. If you don't remember it, don't pressure yourself too much. So the only thing I need to do, because this is 2 moles, is that I have this and I have the double bond, and then I have that, right? So if I cleave it this way, that's how I get 2 moles of the ketone. This is actually acetone, which you already used in lab so many times. I'm going to remove this line. The next reaction is hydrogenation. Forgot to put the question mark. So hydrogenation, again, I'm going to start with an alkene, so I can put my double bond anywhere I feel like. Today, I feel like a lefty, I'll be a lefty. If I feel righty, I'll go for right. So in these kind of reactions, you only have to remember what the reagent does, okay? Syn addition, Markovnikov addition, all of those kind of things, you don't have to write the mechanism, okay? I didn't give you any hydration, but hydration would work the same way. So let's say that I gave you something like this. And I gave BH3, THF, and I ask you what the product is. Then you're going to have to write anti-Markovnikov here. Anti-Markovnikov is this. You have to be careful. That's something you have to memorize. Okay, what the reagent is doing, is it giving Markovnikov or anti-Markovnikov and all that? Okay, so those kind of things you have to memorize. So I want to take a few more minutes and do some multi-step synthesis, okay? Because multi-step is also going to be on this exam, okay? Whether it's a multiple choice or whether it's a short answer question. I will not give you something complicated, okay? I promise you that, but it's going to be everything that you have done, okay, before. So let me take something simple, okay? And let me show you what a multi-step synthesis will look like, okay, for you. So here. And I'm not going to ask you for the answers because at this time, I know it's hard for you to remember all the reagents, okay? So just stay with me and just listen to what I'm saying, okay? Tomorrow or Saturday, it's going to make a little bit more sense to you when you've gone through your notes and looked at the reagents again. So here, what I'm asking you is for the reagents, okay? So I've given you all the products here, and I'm asking you how to do these conversions. And now this is called a multi-step, right? Because you have more than one step in here. So this first one that you have is an epoxide. Those kind of things you have to remember, okay? And the last one is a diol, but not just any diol, it's actually a transdiol, which you can get only from an epoxide anyway. So now for the answers, MCPBA, it's the perbenzoic acid for the first one. And the next one then is hydrolysis. That's it. So this is asking you for a reagent. The other way of asking a question is that I can give you the reagents, and then I can ask you what the product is going to be. So let's say you're doing this. And this. So the first reaction you're looking at is actually not an alkene reaction per se. It's actually coming from the previous chapter. And that is an alkyl halide. You're treating that with T-butoxide. As soon as you see T-butoxide, think elimination, okay? And then also there is the heat symbol there. The heat symbol tells you it's elimination. So it means you're getting an alkene. Also, you have to remember there are only few things you have done. You haven't done any other functional group, right? So with an alkyl halide, the only thing you have learned is substitution or elimination, okay? So don't try to go somewhere where you have not been there, okay? So try to focus on things that we have covered in class. If you give me something that I have not covered in class, I know that you've Googled it. Okay, so the next reaction is then bromine with water. So that is a halohydrin formation. Halohydrin meaning that you have the bromine and you have water. And again, remember, this is anti-addition. So you have to make sure you show me the stereochemistry there.
Just double checking. So that slash is bromine mixed with water.
Yep.
Okay.
Okay. So I have one more type that I want to do with you. And these are one-step synthesis, right? As I said, it's all one step. These ones were little bit more, but not too much more, multi-step. And now what I want to do is like you figure everything out kind of step. Okay, so what that means is here is your starting material, and here is what I would like you to make. And if you think that I am, messing with you, I'm not messing with you. These problems are actually inclined. Okay, in the chapter for alkenes, you will see that I'm getting these examples from the same chapter. So he has done a lot of synthesis also, okay, at the end of the chapter. And at this point, it's not going to be too complicated, okay? Too complicated meaning it's not going to be 5, 6 steps. That's not going to happen right now. It's going to be 2 or 3 step synthesis, okay? So it's not going to be a whole lot. So don't try to make things complicated. I want you to start thinking like an organic chemist, okay? So let me help you with that. With these kind of synthesis, there are 2 ways to do this. You can go forward or you can go backward. Backward, which is retrosynthesis, is actually a lot easier, okay? Because, and it depends actually, I wouldn't say it's easier all the time, but a lot of times it's easier to think backwards because you know what you need to get, okay? So for example, here, let me tell you, you need to be able to get this kind of an alkene because you know that's how you're going to add your Br and OH, right? We just did that up on top. So you know that this is what you need for this reaction. So you at least know this much. So now you're looking at your starting material and you're thinking, okay, I need to shift my alkene because my alkene is internal and now my alkene is external. All right. So now the way you would think about this, hopefully, is that if I'm looking at the alkene here, this is what we would call a Hofmann alkene. And this one here, this is a Zaitsev alkene. And I'm writing product because that's how we've been learning product, but that's the more stable alkene, right? That's Zaitsev's alkene. And this is the Hofmann kind. So to get a Hofmann product, the only way that works is by E2. Which means that you need to do some sort of elimination. So the question is, what are we eliminating? You cannot eliminate alcohols. Alcohols go by carbocation mechanism, which is E1. So which means alkyl halide, okay? So which means that when you're going from the internal alkene to the terminal alkene, you need to be able to remove something. So what are we removing? What are we getting rid of? Well, we're getting rid of an alkyl halide, okay, or a halide. So which means that somehow we need to get an alkyl halide and then do an elimination. That's the thought process. So the alkyl halide, now we can just write the product and see if it works, okay? So this is an alkene. I can add HBr to this alkene, and I will get Markovnikov addition. I don't want to add Br2. Okay, Br2 will give me 2 halides. I don't want 2 halides. I just want 1 halide. So I will add HBr. That gives me the Markovnikov addition. Now, in order to get the Hofmann product, Hofmann meaning the less stable alkene. So the only way you can do that is by using a bulky base and heat. So then this is our 3-step synthesis. So it takes time to kind of learn this. Okay, so I'm not expecting you to master everything, but this is kind of how it works. Okay, so work backward. I have more videos on the page. Okay, on the alkene page, you will see that I have more videos. Okay, so I don't want to talk about everything over here. I've given you an example of like a multi-step thought process. Okay, so there's more videos there. When you get more time, when you're more comfortable with the reagents, then look through that. Okay. So one last thing, absolutely, and you probably keep thinking, oh my God, she keeps just doing one more thing. But I just want to do one mechanism with you, okay? And then we'll call it quits. So the one mechanism that I want to do with you is addition of an alkene, because I don't want you to forget, okay, that mechanisms are also going to be part of this exam. So here is an alkene, H3O plus. So what do you get? So write the mechanism for the product. So this is an acidic mechanism, which means that the only way I can start is by protonating the alkene. So I get my carbocation. Make sure the carbocation is the more stable one. Now you take a second and you look at the carbocation you've made, and you can probably see that I can make it more stable. Okay, so I'll do a methyl shift. Again, don't write that on the arrow. Show the shift. Okay, that's the methyl group that's going to shift. When I give this in class, sometimes I get a different kind of a product, and I can live with that too. And what some people do, because some of you there, you're really into it, and I don't realize it, and I don't think about it too much sometimes, and you end up actually doing a ring expansion. That's also possible, okay? But try to keep it simple, all right? So here, a methyl group is shifting. So now you have a tertiary carbocation. So this is secondary, and now this is tertiary, okay? And remember, our goal is H3O plus, right? So which means we have to get an alcohol as a result. So we are going towards an alcohol. So which means the next step is water attacking the carbocation, which my arrow is just a little short. So you can attack from wherever you want. It's up to you. You can draw a nice long arrow. And so once you have this, then make sure you have the oxonium ion. Don't forget the positive, and then deprotonate, okay? That's it. So that's your product. At this time, this is, what you can expect in any kind of a reaction mechanism, is that if I give you a mechanism, it's obviously going to have some either rearrangement or it's going to have multiple products, right? So in elimination, you can have Zaitsev's product and Hoffman product. In the case of alkenes, or even dehydration, you can get two, right? That's elimination. So in case of alkene addition, again, think about rearrangements and then see, if rearrangement is possible. So usually it will be. Otherwise, what's the point of giving a mechanism? If any one of you think that you will get this kind of a product where this will add to water, okay, and so you will end up getting, and just I'm writing multiple steps here. So if you think that this is the alcohol you will get, you will actually not get that at all. Okay, because the rearrangement is possible in order to give you the tertiary alcohol. So a secondary alcohol is never going to form, okay, in this case. So if I say, give me two products that are possible, you have to rearrange. You have to do the rearrangement first and then think about what other products I'm going to get, okay? So especially if rearrangement is possible. If it's a Zaitsev's product and a Hoffman product, that's a different thing. But if a rearrangement is possible, do the rearrangement first and then think about any other product that you can form. So I know it was a lot today also. Some of it was simple enough, and some of it at the end, I think, was just to give you an idea of what kind of problems you will get for this chapter. So let me stop.